This problem looks simple at first, but there is a little trap hiding inside it. Because the question seems to ask for one area, and I want to know whether the information actually gives us only one possible triangle. So, let me solve it from scratch and be very careful about that. We are told that we have a right triangle. One of its legs has a length of 9 units, and all 3 side lengths have to be positive whole numbers. We need to determine the area. My first thought is that because this is a right triangle, the Pythagorean theorem should be the natural place to start. So I'm going to call the other leg x, and I'll call the hypotenuse y. Remember, the Pythagorean theorem says that in a right triangle, the square of the hypotenuse equals the sum of the squares of the 2 legs. So, in our case, I can write 9 squared plus x squared equals y squared. 9 squared is 81, so this becomes 81 plus x squared equals y squared. Now, I want to isolate the number 81. So I'll move x squared to the other side. That gives me 81 equals y squared minus x squared. And this is where I notice something important. The right side is a difference of 2 squares. Whenever I see something like y squared minus x squared, I can factor it as the quantity y plus x multiplied by the quantity y minus x. So now I have 81 equals the quantity y plus x multiplied by the quantity y minus x. This is really the key observation, because instead of searching randomly for possible values of x and y, I can use the factors of 81. Since x and y are positive whole numbers, these 2 factors, y plus x and y minus x, must also be positive whole numbers. So let's find all the positive factor pairs of 81. There are only 3 possibilities, 1 and 81, 3 and 27, and 9 and 9. Now, I need to check everyone, because finding one valid triangle does not prove that the answer is unique. There could be another triangle hiding in the other factor pairs. Let's start with 1 and 81. I'll suppose that y plus x equals 81 and y minus x equals 1. Now, I have 2 equations, and there is a very convenient thing I can do. I'll add them together. On the left, y plus y minus x gives me 2y, because positive x and negative x cancel each other. On the right, 81 plus 1 gives me 82. So 2y equals 82. Dividing both sides by 2 gives y equals 41. Now I know the hypotenuse is 41. Let me substitute that into the second equation. I have 41 minus x equals 1. Therefore, x must equal 40. So our first possible triangle has side lengths 9, 40, and 41. Before I trust this result, I want to verify it using the Pythagorean theorem. 9 squared is 81, and 40 squared is 1,600. Adding them gives 1,681. Now, 41 squared is also 1,681. Perfect. So, 9, 40, 41 really is a valid right triangle. Now let's find its area. The area of a right triangle is 1/2 multiplied by one leg multiplied by the other leg. So here, the area is 1/2 multiplied by 9 multiplied by 40. I can multiply 9 by 40 to get 360, and half of 360 is 180. So our first possible area is 180 square units. But I'm not going to stop there, because remember, the factorization gave us more possibilities. Let's move to the second factor pair, 3 and 27. This time I'll set y plus x equal to 27 and y minus x equal to 3. Again, I'll add the 2 equations. The x terms cancel, leaving me with 2y equals 30. Divide by 2, and I get y equals 15. Now I substitute 15 into the second equation. 15 minus x equals 3. So, if I subtract 3 from 15, I get x equals 12. That gives me another triangle with side lengths 9, 12, and 15. Now this looks familiar, but I still want to verify it rather than assuming it works. 9 squared is 81. 12 squared is 144. Add those together and I get 225. And 15 squared is also 225. So, yes, this is another perfectly valid right triangle. Now, let's calculate its area. Again, the formula is 1/2 multiplied by the first leg multiplied by the second leg. So the area is 1/2 multiplied by 9 multiplied by 12. 9 multiplied by 12 is 108, and half of 108 is 54. So this triangle gives us an area of 54 square units. At this point, we already have 2 different answers, but I still want to check the final factor pair, because we need to make sure we haven't missed anything. The last pair is 9 and 9, so suppose y plus x equals 9, and y minus x also equals 9. Now look carefully at these 2 equations. If I subtract the second equation from the first, the y terms cancel. I'm left with x minus negative x, which is 2x. On the right, 9 minus 9 is 0, so 2x equals 0, which means x equals 0. But that cannot represent a triangle because the side of a triangle must have positive length. Our original condition also specifically says that all 3 side lengths must be positive whole numbers. So this factor pair gives us a degenerate case, not a valid triangle, and we reject it. Now everything starts to make sense. We didn't find just one possible triangle, we found 2. The first triangle has side lengths 9, 40, and 41, and its area is 180 square units. The second triangle has side lengths 9, 12, and 15. And its area is 54 square units. And both triangles satisfy every condition we were given. This means the original information is not enough to determine one unique area. The area can be 54 square units or 180 square units. And honestly, I think that is the most important lesson in this problem. When a question appears to ask for a single numerical answer, I should never assume that one solution is automatically the only solution. I need to check whether the conditions allow other possibilities. Here, the breakthrough was recognizing the difference of 2 squares, turning 81 into the product of y plus x and y minus x, and then systematically testing the factor pairs. If I had stopped after finding the 9, 40, 41 triangle, I would have incorrectly claimed that the area was 180 square units. But checking the remaining factors reveals the second triangle, 9, 12, 15, with an area of 54 square units. So the final answer is not one unique area. There are 2 possible areas, 54 square units and 180 square units. That second triangle is exactly what makes this problem more interesting than it first appears.